Did you know that a single drop of hydraulic fluid pressurized to the levels found in a modern jetliner can escape a pinhole leak at nearly the speed of sound? That tiny stream of liquid can slice through a wooden plank like a laser beam. It can, and has, injected itself directly into a person's bloodstream, a catastrophic injury that is often fatal. This isn't just about moving parts. It's about harnessing a force of nature that is both immensely powerful and incredibly dangerous. When we talk about hydraulics, we are talking about a technology that allows a pilot's gentle touch on a control stick to move a 100-ton aircraft with precision and grace. It's the hidden circulatory system, the silent, powerful muscle that flexes to bring a plane's wings, wheels, control surfaces to life. So, what exactly is this incredible system? At its core, hydraulics is beautifully, elegantly simple. It's the science of putting a liquid under pressure to do work. Think about squeezing one end of a water balloon and watching the other end bulge out. Let's get our hands dirty and look at the actual components, the nuts and bolts of a jet's hydraulic system. The heart of the system is the reservoir. It holds the hydraulic oil, lets air bubbles escape, and helps cool the fluid. Think of it as the system's lungs and its radiator. From there, we have the pumps, often driven by jet engines or by electric motors. They pressurize fluid to 3,000 to 5,000 psi, over 100 times car tire pressure. Once pressurized, the fluid moves through lines and hoses, steel, titanium, and flexible rubber, the arteries. But you need control. That's valves. A pilot's input becomes an electrical signal that tells a valve to open or close, sending fluid only where it's needed. The business end is the actuator. It's a hydraulic cylinder with a piston inside. Fluid into one side pushes the piston, which moves things like a landing gear leg, a wing flap, or a rudder. So, how do we get from a quiet tank of oil to the brute force needed to move a 50-ton landing gear against a 200-mile-per-hour wind? The power generation starts at the source, the aircraft's main engines. Most large aircraft use engine-driven pumps. A gearbox spins the hydraulic pump, converting rotational energy into hydraulic pressure, efficiently using energy the engine already makes. This is the primary source during flight, a constant, reliable flow. But what if the engines aren't running at the gate? Or if an engine fails? Enter other pumps. Most aircraft also have electric motor pumps, powered by the aircraft's electrical system. They provide pressure without a running engine, essential for ground ops and backup. Many aircraft also carry a ram air turbine, the RAT, a small propeller that deploys into the airstream. The wind spins the RAT, driving a small hydraulic pump to power flight controls. It's the ultimate get-you-home device. Force equals pressure times area. Imagine 3,000 pounds per square inch. Now send that to a piston with 10 square inches. 3,000 times 10 equals 30,000 pounds of force. All started by a tiny electrical signal opening a valve. That's force multiplication. A pilot's small, precise input becomes massive force. Section 4. Redundancy is my only God. The gospel of hydraulic safety by design. In aviation, the mantra is, never trust a single point of failure. For engineers, it's all about redundancy, redundancy, redundancy. You never, ever have just one. Large jets typically have 3, or sometimes 4, independent hydraulic systems. They are color-coded or named green, blue, yellow, and designed to be entirely separate, each with its own reservoir, pumps, lines, and fluid. The genius is how they share the workload. Each system might power different things, but there's always overlap for the most critical functions. For instance, green might power landing gear and a left aileron, blue the rudder and right aileron, yellow the brakes and backup paths. If you lose an entire system, say a ruptured line dumps green fluid, the plane can still be flown safely. Redundancy extends to power sources, engine-driven pumps, electric pumps fed by generators, the APU, and even the RAT. United Airlines Flight 232 highlighted a vulnerability now mitigated by more line separation, better shielding, and smarter isolation logic, making total hydraulic loss astronomically improbable. Section 5. Handle with extreme care the human factor. As much as I love power tools and powerful machines, I have a deep respect for the dangers they present. A jet's hydraulic system is at the top of that list. The most immediate danger: high-pressure injection injuries. A pinhole leak can pierce skin like a hypodermic and inject toxic fluid. Leaks create severe slip hazards and serious fire risks near hot engines, brakes, or electrical arcs. Meticulous cleanup and immediate repairs are critical safety procedures. Fluids like Skydrol are chemically aggressive. They can irritate skin and eyes and damage plastics and paint. Technicians must wear the right PPE, nitrile or butyl gloves and splash-proof goggles, not any old shop glove. Section 6. The rules we live by. Maintenance and safety protocols. The first and most sacred rule: bleed the pressure and verify 0 psi. Then enact lockout, tagout so systems can't be re-energized. Handle fluid with dedicated, scrupulously clean containers and funnels to prevent contamination. Clean spills immediately with approved absorbents and dispose of oily rags in sealed metal containers. Ultimately, rigorous training and disciplined vigilance keep aviation's hydraulic muscle both powerful and safe.